This is a narrated video series on the subject of IBM's WebSphere Java Batch. My name is Don Bagwell and I'm from the IBM Advanced Technical Skills Organization in Gaithersburg, Maryland. This is part 3 of the series. In this part, we provide a closer look at some of the key features of IBM WebSphere Java Batch, and in particular, features new to ComputeGrid version 8 and WAS version 8.5. One of the fundamental elements of transactional batch processing is the ability to take checkpoints during the job. Ideally, the batch container provides this service, and that's exactly what WebSphere Java Batch provides. Imagine a Java Batch program operating within the container environment we described in part 2 of this video series. The checkpoint processing property is specified in the XJCL file for the batch job. The XJCL property allows you to specify the type of interval, record or time-based, as well as the value. When the job is submitted, the batch container becomes aware of the checkpoint property in the XJCL. Here we're showing an example of checkpointing every 5 records. Checkpointing every 5 records is an unusually low number, but for the sake of illustration, assume that's the number. As the batch data stream works through the records, it performs commit processing every 5 records because that's what's specified in the XJCL. And for every checkpoint interval process, the last good checkpoint is persisted to one of the WebSphere Java Batch control tables. This is so a job restart may know where to pick up and begin again. So in summary, the checkpoint processing is supplied in the XJCL. Checkpoint processing is a function of the container, not the batch program. Remember, the batch program focuses on the business logic. The batch program gets invoked for every record processed by the batch data stream. The checkpoint processing is occurring as a service of the container. The batch program stays focused on the business and does not itself worry about checkpointing. As checkpoints are reached, the value is persisted to the database, so job restarts may begin again from that point. The value is stored because a job restart may occur at any time after a job goes into a restartable state, 1 minute, 1 hour, 1 day later. What's more, the job restart may take place in a batch endpoint server different from the original. Having this checkpoint value persisted allows the greatest flexibility for job restart. This illustration shows a checkpoint interval of every 5 records. That's probably too low a number for most real-world scenarios. The checkpoint interval you set is based on your knowledge of the balance between recoverability and efficiency. Set the number too low and too much commit processing takes place. Set the number too high and you risk losing a lot of work if the container is forced to exit and roll back to the last commit point. Skip record processing is a feature new to ComputeGrid version 8 and WAS version 8.5. It provides a way to keep processing a job even when a data read or write exception occurs. With this feature, read or write exceptions will not surface up to the application. Like checkpoint processing, skip record processing is a function of the container, not the batch application. Properties you code in the XJCL for the job tell the container how the skip record processing is to behave. For example, whether record skipping will take place, and if so, how many records may be skipped before exceptions are passed up to the application, and what exceptions to include or exclude from consideration. The purpose of this feature is to allow a job to continue on when an occasional read or write exception occurs. Failing the whole job because of a rare read or write exception would mean a lot of time is lost manually restarting the failed job. It does this by consuming exceptions down at the batch data stream framework layer. Your batch application does not see the exceptions. You may wonder how you would know which records are being skipped. That's the role of a listener function that calls code you write whenever a record is skipped with this feature. Your code would then log information about the record that was skipped. Properties in the XJCL control the behavior of this feature. As mentioned, you indicate how many records may be skipped. After that limit is reached, exceptions bubble up to the application. You get to indicate what exceptions to include for skip record processing. The alternative is to specify which exceptions to exclude. At some point, the number of records skipped may exceed what you think is the appropriate limit for this type of feature. Once the limit is reached, any further read or write exceptions will surface up to the application. If the batch application does not handle the exception, the job will fail and go into a restartable state. All the normal rollback to checkpoint processing would take place. Another new function in Compute Grid version 8 and WAS version 8.5 is a companion to skip record. The retry step processing provides a way to automatically retry a job step when an exception is thrown by the batch application itself. Like skip record, this is controlled by properties you set in the XJCL for the job. You indicate whether retry step processing will take place, how many retries of a step are permitted, and what exceptions to include or exclude from consideration. The objective is to avoid failing a job and putting it into a restartable state just because there was an unhandled exception. The goal is to provide for the job to survive the occasional exception. This feature is similar to skip record, except that it takes place at a higher level. Skip record is designed to protect the job against exceptions thrown by the batch data stream framework. Retry step operates at the level where your batch step code is executed. When a batch step exception is thrown, the container will roll back to the last good checkpoint position. When the step is automatically retried, the container restarts from that checkpoint. The container will call a listener program you provide when a job is retried. This gives code you write the opportunity to log information about the exception that occurred. Properties you supply in the XJCL indicate how many retries are permitted and what exceptions to consider. If the retry limit is reached, then the job goes into a restartable state. Restarts after that would require manual intervention. But if this feature helps a job survive a few exceptions with automatic retries that allow the job to run, then it means your batch processing completes in a more timely manner. We've mentioned listeners several times so far. Listeners are called by the batch container at certain points in batch processing. This allows code you write to get control so custom processing may occur at that point in the batch job. There are three types of listeners: job listener, retry step listener, and skip record listener. We'll start with the job listener. The container will call your job listener at the start of each job, at the start and end of each job step, and again at the end of the job. You let the container know about your listener code with a property coded in the XJCL for the job. This allows your listener code to do any setup or cleanup work you feel is appropriate for the batch job being performed. Retry step listeners are called when an exception is thrown that triggers retry step processing, and again when the retry is attempted. This requires you to register your listener code to the container. This is done with a small bit of Java in the batch step code. The container sees the registration and knows what retry step listeners are in effect. Retry step listeners may be used to log information about an exception and to provide information about where in the processing the exception occurred. Skip record listeners are called whenever an exception is thrown during a read or write operation that triggers the skip record function. Your listener may then log information about the skipped record. Like retry step listeners, this requires you to register your listener code to the container. Again, this is done with a small bit of Java code in the batch step itself. The container sees the registration and knows what skip record listeners are in effect. In summary, the purpose of these listeners is to provide a way for your code to get control during key points in the overall batch processing cycle. The Parallel Job Manager function of WebSphere Java Batch provides you the ability to split large jobs into smaller parallel sub-jobs. Transactional batch jobs often lend themselves to parallel processing based on ranges of the data being worked on. So imagine a job that processes 1 million records and takes 10 hours of time to run. That's one way you could process the job. Or if the job lent itself to running in parallel and you had enough processor resources to run the job in parallel, you could run 10 sub-jobs in parallel, with each sub-job operating on a 1/10 sub-range of the overall records. The result is, in theory, the job completing in 1/10 the time. Here's how this feature works. First, you specify in the XJCL whether the job step is to run in parallel. The sub-jobs may run in the same JVM but on different threads, or in different endpoint JVMs, or both. You also specify how many parallel sub-jobs you wish to run. The Parallel Job Manager uses this at submission time to split the jobs into sub-jobs. The Parallel Job Manager calls a piece of custom code you write that creates parameters used to split the data into the sub-job ranges. This is custom code because you know your data better than WebSphere Java Batch knows your data. You know how it might best be divided. So imagine the 1 million records we mentioned earlier. Imagine those data records are keyed with customer numbers from 1 to 1 million. If 10 sub-jobs are called for, then the data range might be split based on the customer number. Sub-job 1 would operate on customer numbers 1 through 100,000, sub-job 2 on numbers 100,000 to 200,000, and so on. The parameterizer code you write simply sets up properties that will be used by the subjobs. For example, the parameterizer might create SQL strings for each subjob so that subjob 1 would select customer record where customer number is between 1 and 100,000. That's how the subjob would get only its slice of the data records to work on. When the overall job is submitted, the container sees that parallel processing is called for based on the properties in the XJCL. It calls the parameterizer and then splits the top job into the specified number of subjobs. It dispatches the subjobs and they begin execution, and they work on the data range set up by your parameterizer code. The Parallel Job Manager watches over all the subjobs. It views the separate jobs as part of the larger top job. When all the subjobs complete, then the top job is considered complete. If one of the subjobs ends in a restartable state, then the top job is marked restartable. The objective of the Parallel Job Manager is to give you the ability to split large, long-running jobs into smaller jobs so that the total execution time is reduced. This helps shorten the batch window for that one job as well as any other jobs that may follow. There's no magic to this. It's based first on the nature of the job and the data and whether it lends itself to parallel processing. If so, then the Parallel Job Manager provides a framework in which the job may be split into parallel subjobs. One piece of that framework is the call by the container to your parameterizer code that creates the logic used to select the data ranges for each subjob. The rest of the framework provides facilities to coordinate and manage the subjobs as part of a larger top job. As a reminder, the WP101783 document at ibm.com/support/techdocs has a wealth of information related to WebSphere Java Batch, including a set of 2-page technical brochures, the presentation on which this video was built, as well as a more detailed technical white paper. That is the end of part 3 of this series.